time because I wanted you to practice to seeing the Pythagorean identities. This hexagon may help some of you. It may not help you. Do you have to use it? No. But this is a nice tool to help you have memorized those Pythagorean identities. So, by the way, refresh my memory from geometry. How many sides are there to a hexagon?
6.
How many vertices are there then in the hexagon? How many vertices would then be in the hexagon? 6. How many trig functions are there? 6. So the way the hexagon works is like this. Obviously, you draw a hexagon. Draw your 6-sided figure. I've already drawn one out here for you. In the center of the hexagon, we're going to put the number 1. And then if you're drawing the hexagon on your own, what you would do is you would do from the center of your hexagon, you would draw a radius to each vertice in the hexagon. So now what's happened is you divided the inside of your hexagon into 6 triangles. Then if you were drawing the hexagon on your own, starting at the top triangle, what you would do is you would shade the top triangle and shade every other one. The reason why you want to make sure you shade is because you're only going to work around the shaded triangles. Now what you're going to do is you're going to label each of the 6 vertices with a trig function, and it matters which order you put them in. The first triangle is going to be your 2 most common trig functions, which is sine and cosine. The other 4 remaining trig functions you're going to place alphabetically around the hexagon, starting here at this vertice on the hexagon and going in a counterclockwise rotation. So using the abbreviated version of your trig functions, we've already got sine, cosine. The next one would be your cotangent of x. Then we have your cosecant of x. Then we have secant of x, tangent of x. So any questions on how I've labeled the vertices of the hexagon? Now, let's start by taking a look at this top shaded triangle that I have labeled as a sine x as this vertice, cosine x, and at the bottom is a 1. So the way this hexagon works is this. There's things that you can do. First of all, you can move horizontally. You can go left to right. When you move across the triangle and you go left to right, that means you're going to add the trig functions together. So sine squared, I just did write the square here, sine squared plus cosine squared. What it's equal to is the third vertice of the triangle. So there is one of your Pythagorean identities. Sine squared plus cosine squared. What it's equal to is the third vertice of the triangle. So there's one of your Pythagorean identities, which is right here. You can use those shaded triangles to come up with the alternate forms of the Pythagorean identity. So you're allowed to move across the triangles left to right. The only other direction you're allowed to do is start at the bottom and go up. If you go up, you subtract. So starting at the bottom of the triangle, 1 minus sine squared. What it's equal to is the third vertice of the triangle, which is your cosine squared. So 1 minus sine squared is cosine squared. You can go up the other side of the triangle as well. Starting at the bottom, and like I said, if you go up, you subtract. So 1 minus cosine squared equals sine squared. So there's your 1 minus cosine squared. So this, like I said, may help some of you. It'll take you probably 10 seconds to sketch a hexagon in the corner of your quizzes and tests. And if you understand how to use it, you'll have all your Pythagorean identities right there. All right? I have to show it to my calculus kids too because they have to remember these identities when they come to calculus and they remember the hexagon. All right? Any questions on how that first triangle works? So now let's look at the next shaded triangle. I don't know where, I guess it just didn't copy very well. There it is right there. So my second shaded triangle, notice on the left vertice has the 1, has the cotangent of x, and at the bottom is the cosecant of x. It just didn't print out very well. It's this triangle right here. So same idea. When you go across the triangle, you add. So 1 plus cotangent squared x. When you go down, that's what it's equal to. So 1 plus cotangent squared equals cosecant squared. So there's that other Pythagorean identity. And again, in the hexagon, you can see there's your 1 plus cotangent squared equals cosecant squared. The only other direction you can go involving the shaded triangles is you start at the bottom vertex. And you can go up. If you go up, you subtract. So starting at the bottom, cosecant squared minus 1 is cotangent squared. So cotangent squared is equal to cosecant squared x minus 1. You can also go at the bottom of the triangle and go up the other side. Cosecant squared minus cotangent squared is equal to 1. So like I said, if you start at the bottom and you go up, you subtract. So the only directions you're allowed to do around the triangles, you're allowed to go left to right, which means you add. Or you start at the bottom and you go up, and that means you subtract. So then lastly, it's the last shaded triangle in the hexagon. So notice in this triangle, the vertice on the left is my tangent. Here's my 1, and here's my secant of x. So like I said, if you go across, you're going to add. So tangent squared plus 1. What it's equal to is that third vertice of the triangle, which is secant squared. So there's that first Pythagorean identity. Tangent squared x plus 1 is secant squared. Like I said, you can start at the bottom and work your way up. Secant squared minus tangent squared equals 1. You could also go up the other side. Secant squared x minus 1 is tangent squared x. So the hexagon is just something you can quickly put in the corner of your paper when you're doing a test or a quiz, and then it will help you have all your Pythagorean identities. Because the issue, guys, you have to be careful of is the negatives, which you saw in some of the identities today. All right? You've got to make sure that you get those signs correct, and the hexagon helps you assure that you have the negatives in the correct place. All right? So that's just a tool to help you. Some of you will find straight memorization is the way to go. Some of you will find that the hexagon will work better for you. So it just depends upon what you're more comfortable with. As long as you know those Pythagorean identities, we're good. All right, let's now take a look at, go back to page 6. We didn't talk about dealing with identities where you had fractions involved that you may have to add or subtract. What is more complicated to do when it comes to fractions? Adding them or multiplying them? Adding. So when you're trying to deal with an identity and you see fractions that are added together, remember what I said. You always pick the more complicated side. It's always more complex to deal with adding fractions than it is to multiplying. So I'm going to go ahead on page 6 of your notes. I'm going to do B first. So you agree with me that obviously the more complicated side is going to be the right-hand side. So the right-hand side, I have two fractions that are being added together. if you look at where you're trying to get to, you do not have two separate fractions. Somehow, some way, you're going to have to condense this down to a single fraction. So the only way you can do that is to add fractions together. Now, refresh my memory. How do you add fractions together? What do you have to have? Common denominator, exactly. So looking at these two fractions, remember, every factor has to make an appearance in the LCD. So one of your denominators has a factor of 1 minus sine x. So 1 minus sine x has to be in your LCD. The other fraction has an denominator of 1 plus sine x. So 1 plus sine x also has to be in the common denominator. So what you need to do, first of all, in order to start proving this identity, before you can do any trig identity substitutions and all that stuff, what you need to do is you need to go through the algebra process of adding these two fractions together. So remember, in order to add two fractions together, you have to rewrite each fraction with a common denominator. So look at your first fraction. You already have a 1 minus sine x on the bottom. What's missing to give you this common denominator? You're missing the what? 1 plus sine x. So this is where you have to multiply the numerator and denominator by the missing factor. So all this first step is going to be is me rewriting the fractions with an LCD. So again, I multiply the top and bottom by 1 plus sine x. Look at your second fraction. You already have a 1 plus sine x on the bottom. What's the LCD? What piece is missing that you need in this denominator? You need the what? You already have a 1 plus sine x. What piece is missing? 1 minus sine x. So you have to multiply the top and bottom by 1 minus sine x. And this the reason you can just write at least common denominator or rewrite the fractions. So now that the denominators are the same, you can go ahead and you can add the two fractions together. Remember how you add fractions together. You keep the denominator and you add the numerators together. Well, what are your like terms you can combine? Well, I can add 1 plus 1 together. What is 1 plus 1? 2. And then what happens with your plus sine x and minus sine x? Cancel out, exactly. So here I just added the fractions together. So now remember where we're trying to get to. Somehow, some way, we're trying to get to a secant squared. So the only thing now what you're going to have to do is you are going to have to FOIL these denominators together. Because notice, where I'm trying to get to, I do not have two binomials in the denominator. So I'm going to have to FOIL 1 minus sine x times 1 plus sine x. So I have 2 over. So 1 times 1 is 1. Minus sine x plus sine x cancels out. The outers and inners are going to cancel. And what happens when I multiply negative sine x times positive sine x? That's going to give me a minus sine squared x. And that I just FOILed. When you are dealing with these identities that involve adding fractions, there's going to be more steps. Because the first 3 or 4 steps is just going to be adding those fractions together. So these are going to be longer than the other ones because the first couple steps is still going through the process of adding the fractions together before you can actually get into identity substitutions. Now, looking at the bottom, you have a 1 and a trig function squared. Where should you be looking to do a substitution? Look at your what? Pythagorean identities. What is 1 minus sine squared equal to? 1 minus sine squared is a what? Cosine squared. And that was your Pythagorean identity. Well, I know 1 over cosine squared x is equal to what? By your reciprocal identities. What is 1 over cosine squared x equal to? 1 over cosine squared is equal to what? Secant squared. Where are you trying to get to? You're trying to get to a what? 2 secant squared. So this is actually equal to 2 secant squared x. So like I said, when you're dealing with fractions that are added together, it's going to be a lot longer of a process because the first couple steps is going to come from adding your fractions together. All right, so any questions on 5b? Okay, so for 5a, what I want you to do is, first of all, look at this problem for me for a minute and identify what the LCD is going to be. See if you can identify what the least common denominator should be in 5a. So look at those two fractions for a minute and tell me what you think that least common denominator should be. So think about it for a minute. Look at those two fractions and see if you can think about what the least common denominator should be. What are your thoughts? What's the LCD going to be here? What's the LCD going to be for 5a? What do you guys think? But it's not multiplication. Remember, you can't cross, it's only if you're multiplying can you cross cancel. So what do you think the LCD is going to have to be? 1 minus cosine theta and a sine theta. So any questions, first of all, on what the LCD is going to be? That's why I gave you that worksheet at the beginning of the unit going over rational expressions, because you've got to remember how to do them. All right? So now, in your first fraction, you already have a 1 minus cosine theta. What piece is missing that you need from the LCD? What do you have to multiply top and bottom by? You have to multiply top and bottom by what? You already have a 1 minus cosine. What piece do you need? Sine. So you have to multiply top and bottom by sine theta. So that'll give me a sine squared theta on the top over 1 minus cosine theta times sine theta. Plus, you already have a sine theta on the bottom. What piece is missing that you need? You need a what? You already have the sine theta. What piece is missing that you need to get the 1 minus cosine theta? So you have to take 1 minus cosine theta and multiply it by itself. And this is just your LCD. I already have a sine squared. There's no more simplifying I can do. Before you add these fractions together, you want to make sure you simplify the numerators as much as you can. So you are going to have to FOIL 1 minus cosine theta times 1 minus cosine theta. So I have the sine squared plus 1 times 1 is 1. Minus cosine theta is a minus 2 cosine theta. And then a negative cosine theta times a negative cosine theta is a positive cosine squared theta. And again, you can condense this to one big fraction. And here you can just write add. Like I said, when you're dealing with the fractions that have to be added, there's going to be additional steps because you have more algebra to do in the beginning to bring these fractions together as one. All right? Now look at, if you're on top of everything and you recognize your Pythagorean identities really well, what is sine squared plus cosine squared equivalent to? 1 by your Pythagorean identity. Remember, sine squared plus cosine squared by your Pythagorean identity is equal to 1. So I have 1 plus 1 minus 2 cosine theta all over 1 minus cosine theta times sine theta. And this is your Pythagorean identity. Now what else can you do in the numerator now? What can you now add together? You can add together the what? What can you add together? What's 1 plus 1? 2. Now look at where you're trying to get to. Now it's kind of a good idea to kind of say, okay, where am I going to go from here? Well, look at what we're trying to get to. We're trying to get to a 2 cosecant theta. Notice the 2's are now making an appearance in the numerator. Well, cosecant, remember, is equal to 1 over sine theta. So I have a sine theta on the bottom, and I see the 2's start to make an appearance. So now, remember, after you get done adding fractions together, you always want to make sure, if you can, to simplify them. So remember from algebra land, you always try and simplify by factoring. Is there something you can factor out of this numerator? Is there a GCF you can pull out? 2. And this I just did a factoring. Now, after you factor out the 2, what do you notice you can cancel out? You can cancel out the what? 1 minus cosine theta. Now, like I mentioned, 1 over sine theta is equal to what? Cosecant theta. So then you're done. So 2 times your cosecant of theta by your reciprocal identity. Like I said, this is like the worst case scenario when you're dealing with fractions that you have to add together. Because the first 3 or 4 steps are algebra. Because you've got to add those fractions together and get the common denominators. All right? So that's why, guys, I can't emphasize enough. If you're struggling with rational expressions, that worksheet, you're going to see that it's coming up. I don't pick these algebra topics at the beginning of a unit just for random reasons, because this is the algebra you have to be comfortable with. So if you're still struggling, get in here for Brilliant Blocks so we can practice this rational stuff. All right, so any questions on that one? Again, those are definitely the more challenging ones, for sure. All right, so now let's take a look at letter G. Letter G, see if you can do letter G on your own. Take a little break from the adding ones. There's no fractions to add together. Which side looks more complicated? What side looks more complicated? The left. Again, we've got a cosine squared over 1 minus sine x. So first of all, let's start with the left. Well, G, I've got this cosine squared on the top. I have a whole bunch of sines. So somehow, some way, let me try and get rid of cosine squared and get it in terms of sine. So go to those Pythagorean identities. What is cosine squared equivalent to? Cosine squared is equivalent to what? 1 minus sine squared x. And that's just your Pythagorean identity. Now, look at where you're trying to get to. You're trying to get to somehow, some way, a 1 plus sine x. How the heck do I get to a 1 plus sine x from this mess? Well, look at this denominator that I have. It would be really nice if somehow, some way, I can cancel out this denominator of 1 minus sine x. Look at the relationship between this 1 plus sine x and 1 minus sine x. Now look at this numerator of 1 minus sine squared x. Look at the factoring, because really what you have is this numerator is a second power. You're trying to break this down to a power of 1 sine x. And the only way you can do that is by factoring. So 1 minus sine squared x. How could you factor 1 minus sine squared x? Is 1 a perfect square? Yes. Is sine squared a perfect square? Is it separated by a subtraction sign? Yes. So I'm going to go ahead and I'm going to factor. So this becomes 1 minus sine x times 1 plus sine x, all over a 1 minus sine x. And this I just factored. Now, after I factored this, can you simplify the fraction? What can you cancel out? You can cancel out the what? 1 minus sine x. So I'm left with a 1 plus sine x. You write cancel or simplify. Okay? So like I said, if you see a fraction, sometimes what you have to do after you do a Pythagorean identity substitution is you've got to do some factoring. Okay? Look at H. So letter H, notice I've got another type of fraction. Yes, I know the temptation would be to go to your Pythagorean identities and look, and I'm not saying you can't do this, The temptation would be seeing the secant squared x minus 1 and replace it with a tangent squared. There's really two ways you could go about doing this, and I'll show you both ways. So the first way, doing your Pythagorean identity substitution, tangent squared x over secant squared x. And this is a Pythagorean identity. Notice where you're trying to get to. You're trying to get to a sine squared. So this is where the next best strategy to do, try changing everything into sines and cosines. So I know tangent squared is equal to sine squared x divided by cosine squared x. And I'm just going to write my division problem out horizontally. How do you divide fractions? Multiply by the reciprocal. And again, I'm just going to write divide. Remember, somehow, some way, I want to be left with just a sine squared x, which I have in this numerator. So now, any thoughts on what you can do next to get you rid of that cosine squared that you don't need? Well, what is 1 over secant squared going to be equivalent to? 1 over secant squared is what? Cosine squared. Remember, that's a fraction over 1, and that's your reciprocal identities. Now, after you change 1 over secant squared into cosine squared, what happens now when you multiply these fractions together? What can you cross cancel? You can cross cancel the what? Cosine squares, and you're left with sine squared. And here you just simplified. When you're dealing with fractions in your identities, if you've got two fractions added together, common denominators. Look for factoring after you do Pythagorean identity substitutions. All right? Or like I said, if none of those work, try changing everything into sines and cosines if you have tangents in there. All right? So any questions on that one? You guys go ahead and try number 1 on your own right here.